myself. Okay, okay. Go ahead. I will mute myself.
Okay. Hey, Dr. IPEC. Hey, class. My name's Sam Owens, and I'll be going over the F-15C landing gear. So as for the background, the F-15C, it entered service in 1980. This C model is an improvement of the earlier A model, which came out around 1970. So the goal of this aircraft is it's an air superiority fighter, right? So these go into the battlefield and they clear all air threats, so that then the bombers and the attack aircraft and all that can go in and not worry about any other air threats there to like shoot them down or anything like that. So unlike modern fighters that are like coming out right now, like the F-22 and F-35, these focus on radar and firepower over stealth. Like as you can see by all the hard points and all on the wings, like all these missiles and all that, it has gigantic radar and carries a lot of weapons. So it has 104 aerial victories and 0 losses. This makes it the second most successful fighter aircraft in history, right behind the World War II aircraft, the P-51. The U.S. Air Force operates 249 F-15s, and there are over 500 active around the world right now. As for the performance stats, so it is a very hefty machine. It can carry so much weight, like the max takeoff weight is 68,000 pounds. The max landing weight is 60,000 pounds, and we'll be focusing more on that for this landing gear component because landing, the machine takes and the vehicle takes so much beating that this aircraft needs to sustain. It can go very fast, more than 2 times the speed of sound. It can go very high too. So the picture on the left is actually an F-15C launching a missile into space to shoot down a satellite. So not only can this aircraft shoot down other aircraft, but it can shoot down satellites if needed. Has a very long range, and as you can see by the picture on the right, it can beat up any school bully, no matter how mean they are. So the significance to me, aviation is my passion, right? I grew up around F-15s. My dad was a maintainer on them. As for my goals in the future, I'm in Air Force ROTC right now, and I would like to be an F-15 pilot once I graduate pilot training, which I'll go to after I commission into the Air Force later on this May. And I hope to fly F-15Cs, which is the project I'll be working on. The picture on the left is my first solo when I was 17 years old, the first time I flew an airplane by myself. So design requirements. So this aircraft, it's a landing gear component. We're looking at right here where my mouse is, the very shiny pole. This is the main landing gear support component. Constraints, it has to have high stiffness. We can't have it deflecting all over the place, which could lead to buckling. It has high toughness because this thing takes a lot of heat and a lot of wear and tear. It needs high compressive strength so it doesn't crumble. It needs very high yield strength so it doesn't fail by all the moments, kind of like shearing it off. Dimensions are fixed by the manufacturer. It has to be resistant to creep. So 300 degrees is about the hottest that I can get. So the melting point has to be 3 times that. The melting point of the material has to be over 900 degrees Fahrenheit. And has to withstand the normal operating temperatures of between -50 degrees Fahrenheit and 300 degrees Fahrenheit. As for the objective, we're trying to minimize cost, mass, and embodied energy, but mostly mass. We need it to be as light as possible so it can focus weight on other things. And the free variable is material selection. So as for the material indices, we're modeling this off a light stiff column and a light tough column. Both of those are from literature, which we'll be following. And I brought in compressive strength versus density. I went ahead and derived that. This is so it doesn't crumble under the stress, so it can fail by buckling and by crumbling. And this instance, crumbling is more of an issue because it's the length is shorter, so crumbling is more. So we're looking at compressive strength. Yield strength versus density. Right here, we're treating it as a beam just because this force can get moments on it. So we're going to treat it as a beam and make sure it doesn't yield. And we're also looking at stiffness at embodied energy. That equation is from literature, and we want to make a machining process or a manufacturing process that's as most friendly to the environment as possible. So as for the first material indices, I use the software. This is the stiffness one, the one we want to keep it pretty stiff. We're looking at 5 main materials. We're looking at magnesium alloys, aluminum alloys, titanium, stainless steels, and nickels. As you can see right here, they're all kind of the same. Stainless steels and nickel alloys kind of fall behind. As for the next one, toughness, This one's probably one of the most important indices just because of how much of a wear and tear it takes. As for this one, titanium comes up as a slight edge, but most of them are pretty similar. As for the compressive strength, this one's for no crumbling like we talked about. Again, all these are kind of on the same level, but titanium does pull up a slight advantage. And then this one's the yield strength. This one's for the when we're treating it as a beam and they're getting all these moment forces on them. Again, titanium looks like the best. Poor nickel has been kind of taking up the rear on some of these. And then aluminum, magnesium are still, and stainless steels actually, are still very reasonable contenders for the best material. Operating temps, this is less of a indice, but just to make sure that they are able to function under the temperatures that this part goes through. Stainless steels are a little more on the worse side for temperatures, but they are in the bounds, so we shouldn't worry about that too much. And then we're looking at embodied energy in Young's modulus. Titanium takes the most energy to produce, and stainless steels take the least energy. And we're looking at price and melting point. This is for creep. There's really no creep concerns here. Magnesium and aluminum have little concerns, but with the factor of safety and all that I put in, it shouldn't be much of an issue. As for price, titanium and nickel kind of are at the top, and aluminum is surprisingly right behind them, and stainless steels are the least expensive. So as for this chart right here, we're looking at which materials are the best to choose. So looking through, titanium looks to be the best. It has the most little green stars next to it. Its only negative attributes are it takes a lot of embodied energy, and the price is a little high. But since we're looking at a military aircraft often take performance more than price and manufacturing attributes. So we're going to choose titanium for this project. All right, so obviously titanium is a non-ferrous metal, so we're going to look at manufacturing processes for that. We're going to treat it as a prismatic cylinder, which I have an arrow pointing to, so we'll have all those manufacturing processes not crossed off to look at. So now we're looking at mass. The mass for this is mainly 10 kilograms or around 20 pounds. It can vary a little bit in there depending on the size that's needed, but most of the time it's around 10 kilograms. And this blocks off powder methods. And then we go over to section thickness. Section thickness really took away a bunch of manufacturing processes just because this is such a thick part for the loads and for the beating that it takes. It's about 8 inches in diameter, and that translates to about 200 millimeters. And that leaves 4 processes: sand casting, low pressure casting, forging, and conventional machining. Moving on to tolerance. The tolerance and roughness values are kind of in the middle for this. Both literature sources online said about 0.3 millimeters, so that's what we kept. And then economic batch size. About 100 aircraft are produced at a time. Multiply that by 3. That means you need 300 components. And there can be more aircraft ordered, so I upped that to 500. But still, forging and conventional machining are in there. And I chose conventional machining. Why? Because if we look back at these charts, conventional machining has a way better tolerance. It has it can be more fine, and so that's why I chose it, just because you want to minimize those little micro cracks that are in there. So my conclusion is on the left, and the literature support is on the right. I chose titanium, and so did the manufacturer, McDonnell Douglas, which is now Boeing. They choose titanium, and they also choose aluminum and magnesium for less load-bearing members due to its density. The density is lower, which means the weight's lower. It's produced conventional machining in the real world, just like I concluded, and then finished by precision machining. And it is also in the real world inspected multiple times to ensure there's none of those micro flaws that could fail the part. It's joined by welding and fasteners in my process, and it's also done that in the real world, and fasteners make it easy to take off for maintenance to be done on the aircraft. Here are some useful links, and that concludes my slideshow.
All right, very nice. Just 2 things. It's very good, honey. Thank you. And this is